Hello! Welcome to another OmniFocus fitness video. Today we're going to be discussing caloric expenditure and how that relates to exercise. We're going to find a way to measure our caloric expenditure during running and walking, outside and inside, in an accurate way. So whatever your treadmill is telling you can be off by as much as 30%. It can overshoot or undershoot your total caloric expenditure during exercise. And you'd probably like to know some way of getting an accurate reading of how much you're actually expending, how much energy you're actually expending. So we're going to go over that. So without further ado, let's get started. Let's go. So first things first, we're going to have to figure out what VO2 is. I'd like to go over what VO2 is. And VO2 is simply the amount of oxygen that we consume during exercise. It's a very basic definition. There are tons of physiological things that happen in the body, but for the purpose of this video, just know that it is the amount of oxygen that is consumed during exercise. And that can actually give us a pretty good idea of the actual caloric expenditure that goes on during steady state exercise. So during, again, running or walking. And we're able to figure that out because of something called the respiratory exchange ratio. Now, I'm not going to go into a ton of detail on that, but for every liter of oxygen consumed, so you're breathing heavy, you're eventually going to use a liter of oxygen, and in that liter of oxygen, it's estimated you're using roughly 5 calories per liter of oxygen. And you're going to be using far more than a liter of oxygen to fulfill your workout requirements, but that's the standard that we're going to be using. And again, that 5 calories comes from the respiratory exchange ratio. I'm not going to bog you down with exactly what that is, but if you'd like to know more details on it, of course, check out the article that's linked below. There you can find out all you want to know about the respiratory exchange ratio and how it relates to VO2. But that's all you need to know for now, because this VO2, we're going to actually use that for an equation. If we can figure out VO2 via this equation, then we can figure out how many calories we expend during exercise. So let's go ahead and look at that. I did mention that we are going to be going over VO2 and how to estimate VO2. Well, there are several different ways of going about estimating VO2, but most of them are a huge hassle. You have to set yourself up with a metabolic cart and go into a breathing tube and all these other fancy equipment that you probably don't have at home, and you probably don't want to go through every time you want to adjust your workout. So the American College of Sports Medicine came up with these metabolic equations and they're very simple, that allow you to get a rough estimate of your calories expended. They are much more accurate than what your treadmill would tell you and give you a decent ballpark figure of your calories expended. Now, there are 2 different equations, because we did mention in the intro that we're going to be talking about walking and running. That being the case, there are 2 different equations, one for walking and one for running. They're both set up the exact same way. However, some of the constant variables have been manipulated to change for each type of exercise. Now we're going to be going over in this video just the running equation. However, if you would like to follow along with the walking equation, please click below in the About Me section. There's the article there. I have the walking equation written down so you can follow along, and it's the exact same procedure for the walking equation, so don't worry about that. That being said, a quick rundown on this equation. Again, we're trying to figure out VO2. And when we're talking about the running equation specifically, you should be, preferably should be moving at above 5 miles per hour. So that ensures that you're in actual running mode.
Hi, real quick to interject for the sake of authenticity and reliability. I'd like to quick mention that I made a mistake here. It's actually not just one foot that's suspended in the air, but actually both feet have to be suspended in the air at some point in the movement in a forward motion. Alright, so that's it. Let's go back to the video.
The ground at any given time, and moving in a forward direction, that gives you a rough idea of actually what is defined by running. Because if you're not running and you're using a running equation, that can skew the results. And the equation can actually be used between 3.7 and 4.9 miles per hour, but the accuracy decreases because that's kind of a middle ground, kind of a gray area. So if you are below 5 miles per hour, but you're still moving at a speed where you're definitely running 1 foot in the air at any given time, then that means that most likely the equation will work out pretty well for you. So looking at the equation, again, we're trying to figure out VO2, and VO2 is going to equal 3 different components. VO2 is made up of, in this equation, is made up of a horizontal portion, a vertical portion, and a resting portion. The horizontal portion takes over, makes sure that we're taking into account forward movement. So when you're running, you're moving forward. Pretty simple. And the vertical portion is going to take over any sort of gradation that you might put on the treadmill. It also takes into account the outdoor running. And I'll explain that a little bit in the next section. I'll explain how to manipulate the vertical portion so that you are accounting for different variables that you might not see on the treadmill. And finally, the resting portion. Our body is not simply designed to just exercise non-stop. There's also a resting portion to our VO2. When we're resting, we're using roughly 3.5 milliliters of oxygen. So they add that component into the equation as well. So that is the rundown on the equation, and now we can move on to actually breaking everything down. We're going to go step by step and figure out exactly what your calories are, what you're expending calorically, energetically, to then make your programming as efficient as possible. Let's go ahead and do that. Okay. This is probably the most important part, the part that you probably wanted to get to. Maybe you just skipped all the way to this part anyways. We're going to go step by step using the running equation. I'm going to explain how to plug into things, how to go through the conversions, and by the end of it you should have your calories. You can repeat this part of the video as many times as you need to make sure that you're getting things accurately, or if certain variables change or you decide to change certain variables. And to do that, for better clarity, we're going to go to a blackboard method. See you on the other side.
Let's go ahead and start by looking at our equation in full. So again, just to reiterate, we're trying to find VO2. Quick switch over here. We're trying to find VO2, and we can do that by computing these 3 different major factors. Again, the H is supposed to represent a horizontal movement, and it is broken up into this constant of 0.2 times the speed of movement. So we're going to be plugging in a speed of movement for here. Then, if you are exercising on a non-level terrain, so if you're going to be using, like, for example, a gradation on your treadmill, or if you're going to be outside, we're going to be manipulating this vertical aspect here, represented by this V, with a constant of 0.9 for the running, and then again, we're going to plug in the speed. So the speed here is going to be the same as the speed over here. Makes sense because exercise speed isn't going to change. And then the G is representative of the actual gradation, so the amount of incline, for example, that you would put on your treadmill. Then this R here is, I've briefly explained, is 3.5, supposed to represent the 3.5 milliliters that we use during rest. So the R representing rest, and that's also a constant based on an estimated use of VO2 during rest, which will also, of course, be factored in along with these two exercise variables. And yeah, that's it. That's the equation. So from there, we're going to look at different factors. So these factors that we are going to talk about, before we actually get into the equation itself, we have to be able to convert these different factors that are going to make up the individual caloric expenditure. So for you, what factors are being used? And it's these factors right here. These factors right here are, if we manipulate these four, we can plug them into the equation and get different numbers based on what we would like to achieve. Your weight, of course, the speed of the exercise, so how fast you're running or how fast you're walking, the grade, so the grade of the treadmill, or I'll discuss how that's manipulated for exercise outside, and then of course the time, the amount of time that you're going to be exercising at that grade, speed, and the weight that you are. And so we're going to go through this together. I'm going to have an example, and you can just follow along, have a piece of paper out, and just kind of do the math alongside. So let's go ahead and do that. All right, so this is our example. We're going to take roughly my statistics. I'm a 240-pound person with a running speed of 6 miles per hour at 3% grade, and I exercise for 20 minutes. Now we're going to figure out how many calories I expend from that, and you'll notice that I'm using the four factors that I mentioned before. Here we have my weight. Here we have the exercise speed, the grade, and the amount of time that I will be exercising. Now we're going to go ahead and start by looking at my weight. Now the thing is with this equation is that things have to be represented in a particular unit type, and in this case we're talking about kilograms for weight. And the equation that we're going to be using is weight in pounds divided by 2.2 being the difference between kilograms and pounds. You again, this is my example, of course, put your weight in here, but if you know your weight in pounds, if you know it in kilograms, then you can go ahead and skip this step, but you'll put 240 pounds that I got up here, and then divide that by 2.2, and that should roughly give you 109.1 kilograms for me. So that's all you have to do. Literally just take your pounds divided by 2.2 and you will have your kilograms, and then make sure that you save that off to the side. Alright, moving on to the second factor, which we know is running speed. So right here. And running speed, we are given, mostly when we talk about running speed, we're talking about miles per hour. And in this equation, again, we're going to have to convert it to something more exact than miles per hour. You can imagine that miles per hour is very broad. I mean, if you're talking about the difference between 1 mile per hour and 2 miles per hour is a big difference. I mean, you're moving an entire mile more per hour. So this equation, because it needs a little more exactness, we're going to be converting miles per hour that you would see possibly like on a treadmill. We're going to be converting that to meters per minute. So instead of the miles, we change that to meters, and the per hour, we're going to be changing that on a minute-to-minute basis. And we can do that because we know if you calculate it out, we know that miles per hour can be converted, 1 mile per hour can be converted to 26.8 meters per minute. And that being the case, we have this equation right here. So we're going to plug in our speed in miles per hour, which is, again, right here. Plug that in here, and then just multiply that by 26.8, which is going to give us our speed in meters per minute. Excuse me. And the example in my case is 6 miles per hour, right here, times 26.8 gives me roughly 160.8 meters per minute. Now you've converted that, now you can put that aside and we'll move on to the next factor. Okay, moving on to the third factor. The third factor is, as we mentioned before, a gradation. So we have to figure out how much of a grade we're going to be using. And in this case, it is dependent on if you're actually going to be using any sort of gradation. Well, let's first cover the treadmill. So if we were indoors and we were using a treadmill, we would use, and in my example, I'm using a 3% grade, of course, again, adjust it to your grade. We can't put, in this equation, we can't put the percent, so we would have to convert that to a fraction, and the only way to do that is by dividing by 100. So that'll give us the fractional grade. So I have a 3%, I plug that in here, divided by 100 gives me 0.03. Now that is only if a person is going to be using a grade. So if you don't use a grade, then of course it's going to be 0. You don't even have to worry about it. However, if you're going to be running outside or walking outside, there are a few studies that show that you can at least somewhat make up, if not make up for the majority of the confounding variables from running outside. So hills, running on grass, running on sand, things like that, by actually adding a 1% to 1.5% grade. So here you would have a 1.5 or a 1.0% grade. And that would account, theoretically at least, for the differences between more controlled indoor running and outdoor running. If you're going to be running on a track, most likely you'd be fine with a 0% just because the track is going to be flat. And finally, covering the fourth factor that we can manipulate is time. Now you might notice that I do not have an equation here, and that is for a very good reason, because the main equation, the VO2 equation, is actually uses minutes. So in this case, most likely you're going to already have everything in minutes, so there's no conversion necessary. Okay, and here we are. We have converted everything that we need to convert, and now we can look at the main equation to figure out our VO2. And again, once we figure out our VO2, we can figure out our calories. So this is the main equation, again, that you saw earlier, broken up into the 3 portions. And here we have our conversions, or at least my conversions for the example that we're using. And let me quick go over here again and make sure that you understand this. So the S is supposed to represent the speed right here. And so we're just going to be plugging in the converted speed in here. Then we've got a constant here, and we've got speed again, which again we just plug in that 160.8 meters per minute. And then we've got our grade, which we find right here. And then if we just look down a ways, then we will see, again, we've just plugged in 160.8. 160.8 here for the speed again, and then the grade of 0.03. And the 0.03 does not have a unit because it is a fractional grade. That's all you need to know. Then if you do all the math and go through all that stuff, then you end up, or at least in my example, you end up with 40 milliliters per kilogram per minute. And we're going to dissect that answer now to then figure out the exact calories. So let's do that. Alrighty, so I did mention that we would, once we have VO2, then we can move on to calories, but there are a few steps that we have to go through because we still haven't added, we did take into consideration grade and speed, but we didn't take into consideration weight and time, and we didn't exactly convert those for nothing. So we have to take those into consideration, and I'll explain why. So our current position after the last step is that we've figured out that our VO2 is 40 milliliters per kilogram per minute. And that is, again, just for my example. I know I keep repeating that, but I really want to make sure that when you're going over this, doing the math yourself, that you're not, freaking out because you're not getting the same answer. You're not supposed to, unless the variables are exactly the same as mine. Most likely the answer is not going to be the same. So this is our current position. We're at 40 milliliters per kilogram per minute, but we have to take into account our weight. So if we're going to take into account our weight, we would put the 40 milliliters, again, and that's per kilogram per minute. So we're going to be taking into consideration this portion right here. And we multiply that by 109.1. Okay, right here. I know it says 0.09. I just rounded, so it's no different. It should be right. So 109.1 kilograms, and that's going to give us roughly 4,363.6 milliliters per minute. So now we've equated for weight. We've taken into consideration weight, and now we can move on to the next step. All right, here we are again, on to our next step. And what we've done is taken into consideration now gradation, speed, and weight, and we still have to take into consideration time. But we're not quite going to do that yet. What we have to do is, if you'll remember, is I did mention that that when we calculate calories, we calculate in liters of oxygen equals 5 calories. Right now, our current state, we are in milliliters, which isn't that big of an issue, but it would completely throw off the equation if we left it in milliliters. So what we have to do is move from milliliters to liters, and we do that by dividing by 1,000. So if we divide by 1,000, we end up with liters, and this is rounded, but this is roughly the liters in the example above. So once we have liters, then we can move on to actually figuring out the calories. Okay, the next step is, as I briefly discussed in the last section, moving from liters, which we know that 1 liter of oxygen consumed is roughly 5 calories from the respiratory exchange ratio. Since we know that, and we are in a current position where we have our liters, we've converted from milliliters to liters, a rough estimate, so 4.6 liters in this example, and then we simply just multiply that by 5. Just multiply that by 5, and that's going to give us calories per minute. So the main thing right now is calories. So we're moving in a direction now where we actually know the amount of energy that we're expending. That's it. Really simple. Again, just like every other step, it's really simple. And finally, this is the final step. Quick recap, we have covered weight, we have covered speed, and we have covered grade. Now we just need to cover the time, and that's what we're going to do here. Remember in the last section that I talked about 21.8 calories per minute. So obviously now we know that we exercised in this circumstance for 20 minutes. So all we have to do is substitute a 20 here, and that's exactly what we do. We take the number of calories that we expend per minute, and we multiply that by the 20 minutes of exercise right here, and then we get 436 calories, well, 436.4 calories total, and that is the number of calories that you've expended for 20 minutes of exercise at a 3% grade, moving at 6 miles per hour, which we converted to 160.8 meters per minute for a 240-pound person. And that is that. That is all you need to know. Hopefully you can trace back your steps if you made some sort of mistake. Keep in mind that I did round on a few of these, so it might be off by 1 or 2 numbers, but nothing too extreme.
I did mention that these equations do have limitations, and that kind of goes without saying, really, because they're just equations. They're just based on an average of possibly thousands of people. You know, they study thousands of people and figure out their VO2s and find basically just estimates on calories, VO2, things like that. So there are certain limitations. I'm going to go over 3 of them here. The rest are found in the article below. The first one would be that the equation is only applies to steady state cardio. So we can't be applying this to like high intensity interval training. We can't be using this for variable training. So let's say you're running at 3 miles per hour for like 5 minutes, and then you decide to run for like 12 minutes at like 4.5 miles per hour, etc., and just keep bouncing back and forth. It has to be steady state, which means your heartbeat has to stay within plus or minus 5 beats on a constant level. Another thing is that these equations, again, like I mentioned, they were studied on many people and gave an average, but that average was determined in a standard environment. So for example, the temperature in the room when these people were studied on a treadmill to figure out their VO2 and their caloric expenditure, the temperature in the room was possibly around 68 to 70 degrees. So that's a controlled environment, and that's a best case scenario kind of environment. So if your environment is maybe 90 degrees, you're going to see some difference in the amount of breathing that you do, because your body has to adapt to that specific environment, which again could be completely different from the environment that was studied in the actual research itself. And finally, of course, your treadmill, well, in the case of a treadmill, needs to be calibrated correctly. So if you set up the equation to be, okay, I'm running at 5.5 miles per hour at a 2% grade, you can't have the treadmill set to 3.5 miles per hour at a 3% grade. That doesn't make sense. That's going to completely throw everything off. Not to mention, along those lines, also think about the fact that your treadmill should be well adjusted, so things are still working well. So if the belt is somehow catching, or some of the displays aren't working correctly, or if you're holding on to the railings on either side of the treadmill, those will have a huge impact on the actual amount of calories that you're expending. It could be more or it could be less. Again, if you'd like to know 2 or 3 more variables that have an impact on these equations and their limitations, then check out the article below. Moving on. In summary, for the people that don't want to go through the entire video, I will say that if you want to actually figure out your calories, you're going to have to go through the video. But in summary, just real quick, just to get the theoretical stuff out of the way, treadmills are inaccurate up to as much as 30% inaccuracy. They can overshoot or they can undershoot. They typically overshoot, as far as I know. But there are ways of getting around that. There are ways of calculating caloric expenditure in a far more accurate way. That is also kind of a no-hassle way. So it's not just going to automatically count itself, but you can project through something like an equation, a metabolic equation presented by the American College of Sports Medicine. They created 2 equations for walking and running, as well as a few others, but in this video we just talked about walking and running. And those equations give a much better estimate than what the treadmills would give you. And these are applicable not only to treadmills, but also on a track, like a flat track, indoor track, outdoor running. These are going to be a little bit less accurate, but they're still going to be far more accurate than if you didn't measure your calories at all, or what you would see on a treadmill. And they're able to do that because by the amount of oxygen that we consume, so a VO2, measuring VO2, the volume of oxygen intake, and the CO2 release, we're able to figure out exactly how many calories, using the respiratory exchange ratio. We're able to figure out per liter of oxygen how many calories are being expended. And this is a rather standard number. And that standard number can then be used to extrapolate to a massive amount of people. So that's the bottom line. That is the more theoretical information in this video. And again, if you'd like to actually figure out your actual calories used, then you're going to have to go to the step-by-step section of this video. If you found the information useful, please subscribe. It motivates me massively. Even just one subscription makes me extremely happy, because I know that I'm impacting someone in a positive way through science-based knowledge. And of course, please always check out my sources. Please check out all the details. There are far more details in the article related linked below, and there's also a summary section for the people that, again, don't want to go read an entire article. Anyways, my name's Nick, and I will see you in the next video. Peace!